Hey, today we're going to look at the derivatives of the inverse trigonometric functions. Let's start with the arctangent. So we'll let y be the arctangent of x, or the inverse tangent of x. So the tangent of y is equal to x. And you can either think of that as the tangent and the arctangent are inverse functions, and you can take the tangent of both sides, or you can think of it intuitively as y is the angle whose tangent is equal to x. So when you take the tangent of y, you get, of course, x. We can now take the derivative of both sides with respect to the variable x. This is implicit differentiation. And on the left, it's a chain rule problem because y is a function of the variable x. It's not the variable itself. And so you treat that function as if it were a variable. That gives you secant squared y. And then you multiply by the derivative of that function, which is dy dx. And on the right, we're just taking the derivative of x, which is 1. And that gives us that dy dx is 1 over the secant squared of y. But we'd like dy dx to be in terms of x. We can use a trig identity to rewrite the denominator here. And the trig identity is that 1 plus the tangent squared y is equal to the secant squared y. So we have dy dx is 1 over 1 plus the tangent squared y. But the tangent of y is equal to x. And so that gives us that dy dx is 1 over 1 plus x squared. In other words, the derivative of the arctangent of x is 1 over 1 plus x squared. And we won't bother going through the details, but you could do essentially the same thing to find that the derivative of the arccotangent of x is negative 1 over 1 plus x squared. All right, let's see if we can do something similar to find the derivative of the arcsine of x. So we'll set y equal to the arcsine of x. And as before, that implies that the sine of y is equal to x. And we can take the derivative of both sides to get that the cosine of y times dy dx is equal to 1, where the derivative of the sine of y is a chain rule problem. We treat the y like a variable and get cosine of y, and then we have to multiply by its derivative dy dx. Which gives us, after we divide, that dy dx is 1 over the cosine of y. Once again, we'd like to get this in terms of x, and we'll need a trig identity. And if you start with sine squared y plus cosine squared y is equal to 1, you get that cosine squared y is 1 minus sine squared y. Or since the sine of y is equal to x, we have that cosine squared y is 1 minus x squared, which gives us that the cosine of y is the positive or negative square root of 1 minus x squared, which is sort of an unfortunate answer because we don't really want two results for our derivative. We don't want the derivative to be 1 over the positive or negative square root of something or other, because then it wouldn't be a function anymore. They would give two different results for any particular x value. So that's a little bit unpleasant and disconcerting. And to fix it, you have to recall that the sine is not a one-to-one function. It's periodic, so it repeats every 2 pi, and so there are lots and lots of different x values that map to any given y value. And so the sine as it is doesn't even really have an inverse, and in order to construct this function, the arcsine, the inverse sine, we had to restrict the domain of the sine to the interval from negative pi over 2 to pi over 2. And that restricts the range of the arcsine to the interval from negative pi over 2 to pi over 2. And since y is equal to the arcsine of x, that means that y has a value between negative pi over 2 and pi over 2. And the beauty of that is that for any y value between negative pi over 2 and pi over 2, the cosine of y is always positive, which lets us ignore the negative square root of 1 minus x squared and just consider that the cosine of y is equal to the positive square root of 1 minus x squared. Which gives us our answer, dy dx is 1 over the square root of 1 minus x squared. Which is to say that the derivative of the arcsine of x is 1 over the square root of 1 minus x squared. And once again, we'll skip the details, but you can take the derivative of the arc cosine of x in exactly the same way and find that you get -1 over the square root of 1 minus x squared. So far we have the derivative of the arc tangent, the arc cotangent, the arc sine, and the arc cosine. We ought to complete our list here and also come up with the derivatives of the arc secant and the arc cosecant. And it turns out that to actually compute the derivatives of the arc secant and the arc cosecant, you first have to develop some clever tricks that we would only use in this one particular situation, and so it seems better just to skip it. And so I'm just giving them to you here. The derivative of the arc secant of x is 1 over x times the square root of x squared minus 1, and the derivative of the arc cosecant of x is -1 over x times the square root of x squared minus 1. As is so often the case, it turns out that not all of these are of equal importance. In particular, the derivative of the arc tangent of x, extremely important. This is going to come up every time you turn around, so make sure that you absolutely memorize this one. You need to know it without a doubt, tip of your tongue at all times. After that, it's also worth knowing the derivative of the arc sine of x. Certainly it will show up on your homework, but after the homework, still worth knowing this, not anywhere near as important as the derivative of the arc tangent, but you'll find that it makes your life easier now and then if you also know the derivative of the arc sine of x. And lastly, if you really want to go to town, you could memorize the derivative of the arc secant of x. It will show up in second semester calculus in some crazy technique that we learn, in a problem now and then. But if you didn't know the derivative of the arc secant of x, you would also be okay. As far as these other three are concerned, the arc cotangent of x, the arc cosine of x, and the arc cosecant of x, I can't remember ever seeing a problem where it was important to know the derivatives of any of those. I just include them because it took almost no effort to include them, and you may as well have seen what their derivatives are so that there's no mystery. But I wouldn't spend any time learning them. Okay, here's the way it works. Every time you learn the derivative of some new function, you also learn how to take the derivative of that function of some other function. In other words, we're not often going to look at the arctangent of x or the arcsine of x. We'll be looking at the arctangent of some function or the arcsine of some function. In other words, the chain rule comes into play. So take a couple of minutes and see if you can figure out the derivatives of these two functions. Pause the video, and when you're ready, start it back up and we can check your work. Okay, let's look at the first one. As I mentioned, it's a chain rule problem. You have to treat the x cubed as if it were a variable. And if it were the variable, then the derivative would be 1 over 1 plus that variable squared. And then you have to multiply by the derivative of the function that you just treated like a variable. And the derivative of x cubed is 3x squared. We should, of course, simplify, and we get 3x squared over 1 plus x to the 6th. Please don't leave the x cubed squared as an x cubed squared, because if you do, then it makes me think that you don't know that that's x to the 6th, and you need to know that that's x to the 6th. Turning to the function g, it's the same idea. We treat the e to the x as if it were a variable. And if it were the variable, then the derivative would be 1 over the square root of 1 minus that variable squared. And then we have to multiply by the derivative of the function that we just treated like a variable. And the derivative of e to the x is, of course, e to the x. And once again, we should simplify. And similarly, you shouldn't leave e to the x all squared like that. By the properties of exponents, the exponents multiply in that situation, and you get e to the 2x. This is a common property of exponents that will show up all the time, and you want to make sure that you're comfortable with it. And the last thing I want to say is that there's more than one notation for these inverse trig functions. I'm partial to arctangent for the inverse of the tangent function, but some people like tan inverse of x. They mean the same thing. Two different notations for the same idea. Same thing, arcsine of x, sine inverse of x, they mean the same thing. They go back and forth in popularity every few decades, and I've stopped trying to keep up. Use them interchangeably. I will. Whichever way you see them, you should interpret it as the inverse of the corresponding trigonometric function. Okay, those were the derivatives of the inverse trigonometric functions. There is, of course, a homework on it. You should, of course, have fun with the homework. And I am, of course, looking forward to seeing you in class.